Hi there. So right now what I'm going to do is I'm going to talk about section 6.1, which discusses shifts, reflections, and symmetry. Alrighty. So 6.1, shifts, reflections, and symmetry. Okay, so I need you to recall something that we've already discussed. We've already discussed our horizontal and vertical shifts. Recall the horizontal shifts and the vertical shifts. Okay, recall what that did is that translated our graph, okay, with the vertical shifts. If we have a general function f of x and some number k, remember f of x plus or minus k moves it up or down k units. And recall you have the horizontal shifts, that's when you add or subtract within your function, and that's when you go right or left k units. All right, so we've done that in a previous section. Well, what those shifts did is it really just translated our graph up, down, left, right without changing its shape or its orientation, like there's no flipping going on or anything in space. Okay, what we're going to do now is actually do some reflections, etc., where we're actually going to have things move around and changing their shape and orientation in space. So, just so that we can recap this, and let's actually use a new function that we've established. Suppose I have f of x is e to the x. Okay? We know our basic graph of e to the x. That's our general exponential function. Okay? Now, recall we can look at what f of x plus or minus 5, say, looks like. So how would that look? E to the x plus 5 or e to the x minus 5? And remember, when you add or subtract outside of your function, this is your vertical shifts. So it either moves it up 5 units or down 5 units. So let me just redraw this over here. Okay, recall this is the point 0, 1. So if I'm going to graph e to the x plus 5, what I do is I literally move everything up 5 units. So 1, 2, 3, 4, 5. So now we're at our y-intercept of 6. And that's what our graph looks like. In a similar manner, e to the x minus 5, well, you start here and you move down. 1, 2, 3, 4, 5. So now we'll be going through -4, and we can draw our graph. Okay? So that's a recap of our vertical shifts. Our horizontal shifts, remember, that's when you add or subtract within. So for example, if I wanted to look at f of x plus 5, well, what does it mean to compute that? Everywhere where we see an x in our function f, we're going to plug in x plus 5. And in a similar manner, f of x minus 5 will look like e to the x minus 5 power. All right, now let's recall. When you add within, you move it to the left. When you subtract within, you move it to the right. So if I wanted to graph e to the x plus 5, what I would do is take my basic graph and shift it to the left 5 units. So 1, 2, 3, 4, 5. So now I'm going through the point -5, 1. And there's our graph. In a similar manner, if we want to graph f of x minus 5, what you would do is you would take your basic graph and move it to the right 5 units. So now we're going through 5, 1. Okay? So, notice with our horizontal shifts, our horizontal asymptote with these guys is still 0. Okay? Remember what your horizontal asymptote is. Here, as x gets smaller and smaller, notice our function values approach 0. Okay? Now, what would be my horizontal asymptote when I moved it up 5? Well, notice when it goes through 0, 1, your horizontal asymptote is 1 less than that. It's at 0. So here, your horizontal asymptote would be at 5. And here, your horizontal asymptote would be at negative 5. Okay? So that's just a recap. So, to summarize this so far, let us take the following. So, to date, what we have, so to summarize our translations, when we have f of x minus h plus k, you go up k units if k is greater than 0. You go down k units if k is less than 0. You go right h units if h is greater than 0, and you go left h units if h is less than 0. Notice if h is less than 0, that means it's negative. And if it's negative, say, let's just pretend it's negative 4. Minus a negative is plus a positive. So this is consistent. When you add within, you go to the left. Okay? All right, so that's to summarize our translations. Now what we're going to do is reflect. Literally and figuratively, in fact. Okay, so let's take a different graph. Let's consider our square root function. Okay, so f of x is defined to be the square root of x. And what we're also going to want to graph is f of negative x and negative f of x. Okay? So, before we graph either one of these, and I'll do them in a different color and I'll indicate exactly which one is which, let's graph the square root function. Okay? You may or may not remember this graph, but let's plug in some points. Notice we've got domain issues because we're taking the square root. Can only take the square root of positive numbers. So if I plug in x equals 0, I get 0. If I plug in x equals 1, I get 1. Now, I'm going to pick perfect squares just because I've got a very strong lazy streak and we might as well plot points that are more convenient. So the next number I'll take is 4 because I know the square root of 4 is 2. Okay, the next one I would take would be 9, again, because it's a perfect square. So that's our general square root function. Okay, so let's do this guy first. Let's do negative f of x. All right, we'll do him in green. Notice, all I'm doing is putting a negative in front of my function, so literally, this is what it's going to look like. All right, so if we've got negative the square root of x, let's just think about this first. Okay, what are we doing? We're still plugging in our x values, but what's happening to our function values? Aren't we throwing a negative sign in front of each of them? In fact, we are. If you don't believe me, let's just take a few points. Again, I can plug in x equals 0. Well, negative 0 is 0. If I plug in x equals 1, the square root of 1 is 1, but then I have my negative sign hanging out in front. If I plug in 4, well, the square root of 4 is 2, but I have my negative sign hanging out in front. Okay? So, when we were pondering what does this mean, what it's doing is it's keeping my x values the same, but it's changing the sign of my y values. So doesn't that bring them down here? In fact, it does. Let's plot these points and look. I've got 0, 0. Now I've got 1, negative 1. And I've got 4, negative 2. And notice what I did is my graph reflected about the x-axis. Okay? I'll summarize these things momentarily. Now, on the other hand, let's look at f of negative x. Now, I know this is going to seem funky, especially with our square root function, but check it out. Okay? F of negative x. What does it mean to compute f of negative x? It means everywhere where we see an x in our function f, we're going to plug in negative x. So aren't we looking at the square root of negative x? Now, again, I know this looks very strange because you're thinking, wait a minute, you can't have a negative sign underneath your radical. Let's play. Okay? I can certainly take 0 and plug it in, right? Because negative 0 is 0 and the square root of 0 is 0. Okay? Our next natural number to plug in is 1. The thing is if we plug 1 in for x, we're taking the square root of negative 1, which gives us a complex number. The same thing would happen if we plugged in 4, and then any positive number. So we're kind of like, well, wait a minute, this function is not just going to be a dot at the origin. Okay? So let's look at this. Here we replaced y with the opposite of y with the opposite of y. Okay? Here we're replacing x with the opposite of x. Okay? Here's x, here's the opposite, and vice versa. If these were my x values, that would be the opposite. So let's see if we can plug in negatives here. If I plug in negative 1, I'm taking the square root. I've got this negative sign. And for x, I'm plugging in negative 1. Well, negative times the negative is a positive. What's the square root of 1? 1. You see how the same thing happens if I plug in negative 4? Again, I've got this negative sign hanging out in front. Negative times negative is positive. And the square root of 4 is 2. So, what I have over here then is literally a reflection about my y-axis. Okay? So this leads us to our next generality. Our next generality says the following. Given a function f of x, f of negative x takes your graph and reflects it about the y-axis. And in a similar manner, negative f of x takes your graph and reflects it about your x-axis. Okay. Now there's one more topic in this section that I'm going to discuss, and then what I'm going to do is just take a whole bunch of examples and we're going to play around. Okay, we're going to play around with the reflections, with the translations, and all of that fun stuff. Okay, what I would like to do is define two types of functions. Okay, we have things called even functions. And we say that a function is even if it is symmetric with respect to the y-axis. In other words, f of x is equal to f of negative x. Okay, I think our most classic example of an even function is our basic parabola y equals x squared. Okay? Notice if I was able to fold this along my y-axis, one side would fall right upon the other side. They're mirror images of each other. And again, I think you agree whether I plug in 1 or negative 1, 1 or negative 1, my function values are the same. Right? F of 2, for example, is equal to f of negative 2 in this guy. Why? Because you're squaring them. Okay? So that's our classic example of an even function. Now, we also have what's called an odd function. And what we have is that a function is odd if it is symmetric with respect to the origin. In other words, f of negative x is negative f of x. And our most classic example of a function symmetric with respect to the origin is our cubic function. I always call this the John Travolta function for those of you guys who saw that movie Saturday Night Fever. Okay? Now, what does it mean to be symmetric with respect to the origin? Well, what you do essentially is you take one of the arms and you first reflect it about one axis and then the other axis. Okay? So, for example, if we took this arm here and first we reflected it about our x-axis and then our y-axis, yes, that's symmetric. And we could do the same thing, we could go the other way. We could first do the reflection about our y-axis and then our x-axis. But notice we get the same thing. Okay? So, we have an even function symmetric about our x-axis. We have an odd function symmetric about our origin. One very natural question to ask is, well, wait a minute. Why didn't we talk about symmetry with respect to our x-axis? Again, here we did y-axis, there we did origin. So why don't we have a name for something that's symmetric with respect to our x-axis? Okay, a totally reasonable question. Well, let's look into this, okay? Let's draw a graph symmetric with respect to our x-axis. Okay, I think you'll grant me that one side is a mirror image of the other side. So why don't we have a name for this? Precisely because this is not a function. Remember, in order to be a function, you've got to pass your vertical line test. So while this is a very pretty graph of what we call a relation, this is not a function, and therefore we don't have a special name for him. Anyway, I think that's interesting, and I just wanted to point that out to you. So what I would like to do now are just a bunch of different examples, okay? So, my first example is as follows. Suppose I have a function, f of x, and it contains the ordered pair 2, -3. And what I want to know is what point would lie on the reflected graph if f of x is reflected first about the y-axis and then second about the x-axis. Now, if it helps you to draw a picture, I'm all about it. Drawing pictures in mathematics can be one of the most insightful ways to figure out how to solve a problem. Okay, so we're at the point 2, -3. Okay, it's right here. So first, let's figure out what point would lie on the graph if this graph was reflected about our y-axis. Okay, what does it mean to be reflected about our y-axis? Again, here's x, there's the opposite of x. So instead of being at 2, -3, well, we'd still be down here, but we'd be now at -2, -3. Okay, now what if we took this guy and instead we reflected it about our x-axis? Here's our x-axis. So notice here my x value is staying the same. It's my y value that's changing. So now we're at the point 2, 3. Okay, let's take this example then. Now let us say that we have a graph g of t, and g of t contains the point -1, -5. I'm going to say to you, if the graph is even, which other point must lie on the graph? Okay, so where are we? We're at -1, 1, 2, 3, 4, 5, -5. So we have to go back and ask ourselves, what does it mean to be an even function? Oh yeah, it's symmetric about our y-axis. So again, we're at the same level down here, but we need to be right here. So the other point here would be +1, -5. Okay, while we're on this subject, let me ask this. What point must lie on the graph of negative g of t? Okay, well, notice here, we're just taking the opposite of our function value. So our x value stays the same, but we take the opposite of our function value. All right, next. Let's do this example. So what if I say that f of x is equal to, well, it really doesn't matter, 3 to the power of x. And what I want to do is give a formula and a rough sketch of the following. Let's compute f of -x. Let's do negative f of x. Let's do negative f of -x. And finally, negative f of x minus 2. Doesn't this look like a ball? All right, so what I would suggest we do is make a general graph of what 3 to the x looks like, and then let's try to recall what each of these reflections and or translations tell us to do. Okay, so first off, 3 to the x looks very similar to e to the x. Okay, so that's our basic graph of 3 to the x. Okay, so first let's go over here. Let's first write the formula. F of negative x, everywhere where we see an x in our function f, we're going to plug in negative x. So the formula looks like 3 to the negative x. Okay, but what does f of negative x tell us to do? Remember, you replace x with the opposite of x. In other words, you reflect it about your y-axis. So we'll do him in green. So if I reflect this graph about my y-axis, so these x values I replace with these and these over here, I claim it's going to look like that. Cool, huh? Don't even have to plot points. Okay, what is negative f of x? Well, now that just means throw a negative in front of your function. So that's what your function looks like in terms of its formula. In terms of the graph, remember, when you have a negative in front of your function, what you do is you reflect it about your x-axis. So instead of going through 0, 1, we're going to go through 0, negative 1. And that's what our graph looks like there. You good that far? Let's do 2 more here. Now we want to compute negative f of negative x. Boy, oh boy. All right. We're combining these two essentially. So what is that going to look like? Well, I claim you're going to throw a negative in front of your function and a negative up in your exponent. Okay? I'm going to erase these 2 graphs that we just did because I'm kind of limited with the colors that I have. Now I know this looks very confusing on first glance. However, what I want to say is just use your reflections. Now we're reflecting about both axes, right? You always start on the inside, so first we're going to reflect about our y-axis, and then we'll reflect it about our x-axis. So if it helps you to draw it lightly at first, here we're reflecting it about our y-axis, and now we take this graph and reflect it about our x-axis. Well, pretend this is a decent graph. I always get away with it when I say do a rough sketch. All right, last but not least for this problem, we want to compute negative of f of x minus 2. So everywhere where we see an x in our function f, we're going to replace it with an x minus 2, and then we need to throw a negative in front. Now, the formula of that looks so super nasty, doesn't it? But I claim we really don't have to do much work if we know how our translations and reflections do work. Okay, I'm going to erase this again. Okay, why do I say that? Well, look, okay, first off, whenever you do these things, you have to use your order of operations. This is within my function, so I would do this first. What does this say to do? It says to move your graph right to. Remember, when you subtract within, you move it to the right. So, instead of being at 0, 1, we're at 2, 1. So this is it so far. And now we have a negative in front of our function. So what we do is we then reflect it about our x-axis. So here we are at 2, negative 1. And there's our graph. Sweet, isn't it? All right, let's practice a few more. Okay, this one is really kind of a fun thing to do. Okay, so what we want to do is we want to take f of x to be equal to x cubed. And the first thing that we want to do is we want to reflect it about the x-axis And then the second thing we want to do is go up 2 units. Okay? So, what we're going to do is a basic graph, and then we're going to write the formula, because we're going to contrast that with the following. We're going to take the same function, but now the first thing we want to do is go up 2 units, and the second thing we want to do is reflect about the x-axis. So notice we're doing the same 2 things, but we're doing them in a different order. And what I would like us to do is then compare the graphs and the functions. Okay? So let us check this out. Our basic graph of y equals x cubed is as follows. Okay? It's real important to know your basic graphs. Okay? We'll do the green one first. The first thing we want to do is reflect it about our x-axis. Okay? So, and there. That's a reflection about our x-axis. And now what we want to do is move him up 2 units. So, same basic graph. And there we go. Okay? So, if we were to write this in function form, well, to reflect about the x-axis, that means you put a negative in front of your function, and then you move them up 2 units. Okay? Our order of operations follow. You do the multiplication before you do the addition and subtraction. Now, let's contrast that with this other guy. Okay? I'm going to keep our final green graph on, but I'm going to erase our interim. Now what we want to do is take our basic graph of y equals x cubed, but first let's move him up 2 units. So if I move him up 2 units, this is what I look like. And now if we reflect it, notice instead of going through 0, 2, we're going through 0, negative 2. And there's our graph. Notice these are very different graphs. So, how would we show first that we're going to go up 2 units and then reflect? Well, up 2 units, we know we add 2. The thing is we want to reflect this entire graph. So you put a negative out in front. Okay? So I like that example because I think it really gets at the contrast between the order and how you would write their functions. All right. So our next example that I would like to do here, what we're going to do is, let us take this. Suppose this is my function. It goes through 0, 0, 1, 1, 2, 1, and then 3, 2. Oh, we can do more. How about we then go to there? It's like a little step ladder. Okay? Suppose this is my function f of x. What if I want us to graph f of, how about x plus 1 minus 2? How would we do this? Well, when you're given a graph and you have to do these reflections, what you do is you essentially take each point of the graph that you're given and move it in that way. So, do you agree this means left 1 and this means down 2? So I would take this point here, go left 1, down 2. I would take this point here, go left 1, down 2. I would take this point here, go left 1, down 2. Here, left 1, down 2. And here, left 1 and down 2. Okay? So that's how you approach it when you're actually given a graph. Let's just do one more with this. Let's do f of negative x. Okay, we're going to ignore our blue graph now because we're going back to our original f of x function. What does f of negative x say? Well, reflected about your y-axis. So instead of having this arm here, you've got this arm here. And instead of your step ladder going off on your right side, oopsie, your step ladder goes off on your left side. And there it is. All right, one last example in this section. So, here it is. No graph, I promise. We're just going to interpret a few things. So for t greater than 0, we're going to define a function h of t to be 20 plus 54 times 0.91 to the power of t. And what we're going to say is that gives the temperature of a bowl of soup in degrees Celsius t minutes after it's taken out of the microwave. Okay? Now let's talk about this, okay? If you take something out of a microwave, presumably it's hot and it's going to cool off, okay? Let's look and just get a basic idea of this function here, okay? I'm not going to make you graph these things, but it's a great idea to get some intuition, and certainly when we're doing things together, I will do such graphs, okay? We know that this is an exponential function which is decreasing. And we know that our intercept is 54. Not drawn to scale. Okay? Now, what does this plus 20 do? It just moves it up 20. So, it's still going to go down. Now, the thing is, let's talk then about our horizontal asymptote. For just this guy, our horizontal asymptote, now it's as x gets large, okay? Our horizontal asymptote would be at 0. But since we're adding 20, for this graph here, our horizontal asymptote is at 20. Okay? So that's what we're looking at. In other words, this is as time goes on, our bowl of soup is going to cool off to 20 degrees. Okay? So, if I ask you, what is the practical meaning, say, of h of t plus 10? Well, what that means is essentially we're just going to add 10 more to this function. So instead of approaching 20 degrees Celsius, which is room temperature here, it's going to approach 30 degrees Celsius. So it's just going to be crossing then our axis at 84 as opposed to 74. Okay? Just wanted to give you a little bit of intuition, especially since we just finished up doing our exponential functions. So that completes section 6.1.